So last time, what did we do? Last time we did Newton-Euler stuff. And we talked about the SE3 group, which is sort of bread and butter robotic stuff that shows up all over the place. Briefly mentioned, like, there's some other groups that you can make that are interesting, and like a lot of people have gotten into this recently in the last 5 years or so with Kalman filters and making these so-called invariant extended Kalman filters using these tricks. Essentially, another way to think about that is you bury all the nonlinearity in the exponential map, right? So if you can like pose it as a group, even if it's nonlinear, all the nonlinearity is inside that exponential magic. So you can like do all your linear Kalman filtery stuff on the Lie algebra separately, and then map it through the exponential, and that magically accounts for basically all nonlinearity in the problem. So you like magically have this like nonlinear estimator that works amazingly perfectly and is exact, which is a really cool trick. Unfortunately, the same trick doesn't work quite as well for control. It's still like a useful thing to do, but you can't get the magic stuff to happen. But it's still a cool idea. So that should be on your radar. It's a cool idea. And then we did some like examples. We did quad rotors, which are obviously super popular and useful all over robotics. And then we talked about airplanes. And basically all these things are examples of like SE3 systems that use the same Newton-Euler dynamics. And the takeaway is like, once you have that Newton-Euler setup, you can do all kinds of systems by just plugging in different F and taus for that particular system. So for an airplane, you gotta think about lift and drag and propellers. Quad rotors, just propellers. You can add the more aerodynamic terms for that if you want. Also, you can model legged robots this way with massless legs, which is a very common modeling assumption called centroidal dynamics. So it shows up all over the place. Super, super useful stuff. Any questions about that? Yeah.
With the exponential map, is that
so it's not really dynamic inversion. Like all you're doing, it's really a kinematic thing, right? It's about the sort of the configuration variables rather than the sort of dynamics part. The dynamics part is Newton-Euler or whatever, right? That's sort of the dynamics is sort of the F equals ma stuff, right? So that lives like one more derivative sort of higher, right, so to speak. And where those filters are actually, the way those work, has anyone ever used an inertial filter or implemented one where you filter with an IMU? So that's a whole other thing. And it's very weird and sort of not what you would expect. Basically with inertial filters, the filter state ends up being just the pose, like just position and orientation and stuff. And it turns out like effectively you treat the IMU angular velocity and acceleration measurements as effectively control inputs, and they're not the filtered dynamics. The filtered dynamics in these inertial filters end up just being like the kinematics, in which case this exponential trick is exactly what you want, right? That is the filtered dynamics. So it works beautifully in that context, and it's kind of amazing. So that's kind of the part of why that works, is that you're not actually doing the F equals ma stuff in the filter. You're assuming that you basically measure the results of it directly in the gyro and accelerometer, right? So if you have an IMU, the IMU basically gives you the F equals ma stuff. So it turns out like most people don't, like this is the standard thing to do. It's called an inertial filter. And the reason is that it tends to be that the IMU is better than your F equals ma model, right? In practice, basically, like you said, there's model error, right? That's all in your F equals ma stuff. You just have an IMU, and the IMU is reasonably good. You don't have to worry about that. So at that point, it's just kinematics, right? It's like basically just integrating the IMU and like using sensor measurements to sort of like fuse in with that, right? Okay, that was like sort of a. Though the one other thing I forgot to mention last time was screw theory. People asked about this. Screw theory is literally just SE3, and the screws are the Lie algebra, the SE3 Lie algebra, where you've got like the V omega thing. That's all it is. So it's a sort of special case of this Lie group Lie algebra story. And I like said I was going to talk about it last time, and then I realized halfway through that I did not. I realized after, and now this stupid thing went to sleep, and it's not going to work for me. Okay, cool. What are we doing today? So we're going to take a pretty hard pivot today, and get into some like weirder stuff. So like I would argue this is where it's going to become very sort of off the beaten path, I suppose, compared to like what you would get in another dynamic class. Is the Zach version. We're going to sort of take a hard pivot into optimization. So I'm going to argue that basically all the more advanced dynamic stuff that like Hamiltonian, Lagrangian, et cetera, All of that is really optimization, and looking at it from an optimization perspective, I would argue is a lot more insightful and useful, and algorithmically in particular, a lot more useful. It like shows you how to build better sort of solver algorithms and stuff. So we're going to do that. We're going to do basically a couple lectures on like optimization sort of crash course material. And then at the end of that, we're going to do a like crash course on calculus of variations. Has anyone done that before or heard about this before in RoboMath? Yeah, okay. So we're going to do it a different way. And hopefully it makes sense, but it's going to take a couple of days to get to there. Okay, so first we're going to do a notation thing, which is a pet peeve thing of mine. Then we're going to talk about root finding, which you guys have already kind of done on the first homework. This is like how you solve the time stepping equations for like implicit integrators, right? So use Newton, blah, blah, blah. And then we're going to talk about minimization. I think today just unconstrained stuff. And then next time we'll talk about constraints. And this becomes very important for contact dynamics. Okay, cool. So is this working? Yeah, it's working. Okay, cool. So first, notation. Okay, so this is stuff that you will see this done other ways, other places. Those other ways are wrong. My way is the right way. So this is just like notation for writing of derivatives so that we don't sort of, hate each other. And so if you have some f of x, that's a scalar valued function. So Rn to R, so each a vector spits out a scalar. Then we're going to define partial f partial x, aka the gradient, as a row vector. So it's going to be 1 by n. It is not a column vector. That is wrong, no matter what the machine learning people think. Okay, so why is this the case? This is the case because there's there's a like sort of philosophical reason and a practical reason why this is the way this should be. Basically, df/dx, the way to think about what this really is the linear approximation of the function f, right? And the function f eats a vector and spits out a scalar. So to make that happen, so like, okay, so this is the, like another way of saying this is the linear operator mapping delta x's into delta f's. And it's the first order Taylor expansion, right? So like what you're sort of doing, right, is this. If I have this function, this is approximately f of x plus partial f partial x times delta x. So if delta x has the same dimensions as x, for that to work out, partial f partial x has to be a row vector. We agree? And okay, so that's like sort of, okay, cool. So if we agree on that, then the next one is we have some we have now like a vector valued function. So this is like Rm to Rn, say. Then the Jacobian matrix of this guy has to be an n by m matrix. Just same reason. It's got to map delta y's into delta g's. So it's got to look like this. And just for the dimensions to work out, like it has to multiply that delta y and spit out something that's the size of the output of g. So like it has to be that way. And so this is like sort of stupid philosophy, but the real reason you do this is this makes the chain rule still work. If you don't do it this way and you have transposes in there, it breaks the chain rule. And then you have to sit there and debug your messed up transpose bad code. So this is why you do this. So in particular, right, if I want to like compose these two functions I just wrote down, so like do f of g of y and like Taylor expand this guy, it's just the normal thing that I would expect. It looks like f of g of y plus df dx times dg dy times delta y. And this guy is evaluated at y, and this guy is evaluated at g of y. And I can just do the chain rule as expected. You have to be a little careful here still, because you got to make sure you do this in the right order. Basically, it goes right to left, right? Because these things are matrices and the dimensions matter and the order matters with matrices. You got to be careful. But if you go left or right and you use these conventions, then life is good, and you can do this and not want to kill yourself when you debug your code. I have been there before. This is why I say these things. And then sort of if you really want to, we can sort of, for convenience, define some stuff that goes the other way. So if we write it this way with the nabla, then that means the column version. And then the other one that comes up, right, is del squared. And that's going to be this thing. And this is equal to, you know, this guy. This one doesn't matter so much. Do we know why this doesn't matter so much? I can't mess that one up. Why? It's always symmetric. Yeah. And it's always square. So it doesn't really matter here. You basically get away with being sort of a little loose on this one. Okay. All good? This is sort of laying the ground rules. All right. So next up, this is some stuff that we kind of did really quickly. So we'll take one more kind of pass through this. We're going to talk about root finding, which we've talked about a bit. So let's like just kind of formalize some of this stuff a little more. So given some f of x, which in general, this can be now like multi-dimensional or vector valued, we want to find x star such that f of x star equals 0. So like a root of 0 of the function, right? And like kind of the canonical example of this that we've already talked about is the equilibrium point of some dynamics, right? We're trying to find an equilibrium point. This is continuous time, right? And then the other sort of like extremely closely related idea that we should also know about, which we've also talked about, is a fixed point. And the idea there is instead of f of x star equals 0, you get f of x star equals x star. It spits back the argument. So it's an identity, right, at this point. And this guy, from what we talked about before, is the equilibrium point for discrete time dynamics, right? And you'll sort of hear me and like most people use equilibrium point and fixed point kind of interchangeably. They're basically like the continuous time and discrete time sort of analogs of the same thing. And you can pretty trivially go back and forth between these things. Okay, so how do we find these things numerically? We did this before. We talked a little bit, like really briefly, about Newton's method. We're going to do that again, sort of in some more detail, but I want to point out like kind of the alternative thing. The sort of dumber thing you can do, which is sometimes useful, so it's worth knowing about, is this thing called fixed point iteration. Anyone heard of this? Yeah. Okay, so This I'd say is like the simplest solution method. And I think this actually makes a lot more sense in this dynamics context than in general, like optimization and like where people talk about this. It's actually super clear when this should work in the dynamics context. Basically, if you think about f as the dynamics in discrete time and you're looking for a fixed point, if the system's dynamics are stable, asymptotically stable, then all I've got to do is pick a random starting point for x and just keep running the dynamics, right? Just keep plugging it back in and iterating. And like what that's literally doing is just marching the dynamics forward in time, right? If my dynamics are stable, I'm going to land at that equilibrium point eventually, right? So that's it. That's literally what fixed point iteration is. This shows up in other contexts in optimization. This is actually basically gradient descent. It's super, super closely related to gradient descent. This is not necessarily super obvious, but that's basically what this is. With a fixed learning rate, it turns out this is literally gradient descent. There's very, very deep connections between dynamics and optimization, which we're going to touch on, but there's too much for us to do all of it. If you're interested in that idea, come talk to me. This is fun. Okay, anyway. Okay, so basically, if the fixed point is stable, you just have to iterate the dynamics. Until you like settle until so you literally just do like x k plus 1, like, you know, yeah, it's x k until convergence, right? So this is as dumb as it gets. The sort of caveat to this, right, which if you try doing this, you know, in more general contexts and optimization and stuff, this only works if it's a stable fixed point, sort of obviously, once you understand what's going on with dynamics, right? And it also has very slow convergence, which we'll see in a sec. Anyone know how you know if your fixed point is stable in like the sort of general optimization gradient descent context? What does that correspond to? Anyone know? It's very fun. Convexity, which is, yeah, another way of saying that. So if your function's strongly convex, then this is stable and works. And that's sort of where all the theory. So like literally it's a one-to-one matchup between like the convergence theory for gradient descent and convexity and those ideas and like these dynamics ideas, which is super cool. And super recent, like less than 10 years, 5-10 years, people started to use these ideas, these dynamical systems ideas and stability theory and Lyapunov theory, the stuff we've talked about, to analyze optimization algorithms. So like all the theory for accelerated first order optimization methods in machine learning, like Atom and Nesterov acceleration and these things, the sort of like state of the art way to analyze the convergence properties of those algorithms is via turning them into dynamic problems and using all the dynamic stability ideas that we've talked about to like figure out if they're going to converge or not, which is super cool. So lots of interesting overlap and uses for this stuff. If you're into that, come talk to me. Oh, what did I say? Oh yeah, has slow convergence. That's what I meant to do. There you go. Fixed. Okay, cool. So that we'll look at this in a sec. I'll show you an example. The other way to go, which is the better way, is Newton's method. And like we already kind of talked about this, you're going to fit a linear approximation to f of x. Why? Because we know how to solve linear equations. So we're going to sort of approximate it by the thing we know how to solve, and then we're going to solve the approximation as we do this. And then we set this thing equal to 0. And we solve for delta x. So we get, f of x plus partial f partial x times delta x equals 0. If we just rearrange that, we get delta x equals minus the inverse of this Jacobian guy times f of x. And then we sort of apply that delta x correction. So we get like x gets x plus delta x, and then you just repeat this until convergence. Okay, so we're now going to take a look at an example of this, which we kind of already looked at, something like this. Okay, so we're going to do this for the backward Euler integrator, which we kind of did before, but I'm going to specifically look at comparing the this fixed point iteration. So we're going to do it on the pendulum. And as we saw like before, right, like that whole like thing about it, the fixed point has to be stable, blah, blah, blah. Some caveats to that, right? So basically, we're going to do this on a pendulum. And it turns out, right, because the backward Euler thing adds artificial damping, it's sort of more stable, right? So it turns out this actually works kind of well for backward Euler, more so than it might for other integration methods, the fixed point iteration, right? So kind of helping us out, the artificial damping stuff. So let's take a look at what's actually going on in here, maybe. So this is the Newton step. So we've seen this already, right? So this is like what we did for solving implicit midpoint, and we kind of looked at this before. We're going to use forward diff to get the Jacobian. This is the residual for the backward Euler thing, right? I'm evaluating the dynamics at the future time step. And then this is just Newton's method right here, right? And that's it. And this, I'm keeping track of the error norm as I go to sort of like see how it converges. And we're going to take a look at that. This is the fixed point iteration. So I'm literally just plugging it back in over and over again until I hit some tolerance. And I'm going to 1e minus 8 tolerance here, which is not very tight, right? Okay, so let's see, where am I? Okay, so let's run it. Okay, so this is what we expect. This is just wiggles around from some initial condition thing. And they're both doing backward Euler. So the plots are on top to 1e minus 8 tolerances. So they're on top of each other. I get the same answer. That's good. Let's look at the convergence behavior. What is this? Oh, this is the difference between the two solutions. That's not super interesting. Okay, so here's what happens for backward Euler over like the first time step. So it starts out with some error, and you can see like the error sort of gradually decreases until I get down to this like 1e minus 8 tolerance, right? So how many steps did this take? This took 14 steps. How many steps does Newton take? 3. And it like nails it to machine precision, right? So obviously this is quite different. And then to like really drive the point home, I'm gonna plot these, right? So this is kind of the behavior of fixed point iteration. This is analogous to gradient descent in optimization, same thing, right? And this is Newton, basically like bam, nails it to machine precision. So in particular, Newton's method has what's called quadratic convergence rate. Roughly what that means is you double the number of significant digits in your answer every iteration. So if you want to hit machine precision, here we go. Look, we're down at the like 0.1-ish level here. Few significant digits. I double the number of significant digits. So now I'm down to 10 to the minus 6. I double the number of significant digits again. Now I'm down to this like, 1e minus 12, 13, but turns out 1e minus 15 on this problem range. So that's what you can expect with Newton's method when you're close to an answer. So with Newton, you can like legit get machine precision answers all the way to the double precision floating point, precision of your computer pretty easily, like a handful of iterations. With these fixed point methods, these guys have like linear or sublinear in a lot of cases convergence rates, depends on the details of the problem. So these guys, like you can get down sort of into this range pretty easily, but like often getting all the way down to machine precision is just not going to happen. You're going to get to like a handful of digits and then call it good, just because it's going to take forever to do any better. So that is kind of the Newton versus fixed point iteration, Newton versus gradient descent kind of story. Newton always works also, right? Newton, you can find an unstable fixed point as well, because you're not depending on this like iteration scheme to converge, right? Sort of similar to like gradient descent and convexity and blah, blah, blah. Okay, cool. Questions about this? All good? Yeah. So this is the pendulum dynamics. And then here's the actual equation I'm solving for. This is backward Euler. So it says xk plus 1 equals xk plus little time step h times f of xk plus 1. So it's Euler, but I evaluate the dynamics at the future time step. So it ends up being an implicit equation, right? So that's that guy right there. Fixed point iteration, I just take a guess and keep plugging it back in until it converges. And then Newton, I write down this residual equation, right? So this is like xk plus h times f of x next minus x next. So this is just moving everything that I just said to all the right-hand side and setting it equal to 0, right? So it's a root finding problem. I need Newton on the root finding problem. And like, yeah. So the takeaway is Newton's blazing fast and like super good. Fixed point iteration / gradient descent, not so much. Why would I ever use gradient descent or fixed point iteration then? Like, why do we even care? Why do we even talk about it? Why is it still a thing? Yeah. Yeah, that's exactly it. Yeah, JJ, do you have other thoughts? Okay, so same thing. So yeah, basically Newton's a lot more expensive to evaluate a step because I have to evaluate the Jacobian and I have to invert it or solve a linear system involving it. And that scales cubically in the size of the problem. So the bigger the problem gets, so for a few dimensions, Newton's a no-brainer. You should absolutely do it. If your problem gets to, even for like thousands of dimensions, it's also a no-brainer, like with modern computers, no problem. When you get to like millions or tens of millions, that's where it sort of becomes intractable. And you then want to look at first order methods. So this is why in deep learning, we use first order methods, right? And people spend a lot of time trying to make the first order methods go faster, right? That's what all this Adam, Nesterov acceleration stuff is about, because they're slow and they don't converge super well. So there's like but it basically for problems like less than 100,000 dimensions, say, like Newton all the way. As long as that Jacobian will fit in memory, you should do it, and it's better. Okay, cool. Right, I need to hide this. Okay, back to this. Okay, so we talked about okay, cool. So let's see. Summary. To summarize that whole conversation, you get quadratic convergence rate, which is awesome. You can achieve machine precision, which we just did, right? Everyone knows, yeah, double precision floating point is about 15, 16 digits. So 10 to the minus 15 is as good as it gets. And then the kind of the main thing is the most expensive part of this is solving that linear system, which is order n cubed. So if n is big, this is gnarly. And then the other sort of thing is that, which we will talk about, is you can actually improve on that significantly, which hopefully we'll get to in here, by taking advantage of problem structure. Hopefully more later. So in particular, it turns out dynamics, sort of standard rigid body dynamics, et cetera, always order n cubed if you do it naively. But you can do it, it turns out, for at least for serial chains. People probably heard about this. You can do it in order n time, linear time. That's Featherstones algorithm, right? You guys have heard of this. So there are basically wins to be had here by taking advantage of like the kinematic tree structure of your robot, et cetera, and you can get it to go from cubic to linear, which is huge for a complicated system. Okay, cool. Any other questions about this? Yeah, I want to do that. We're gonna hopefully do Featherstone this time. If I can like keep us on track. It's gonna be a while though. Okay, cool. So like, so we did root finding. We're gonna talk about minimization. So this is sort of the bread and butter of optimization, unless you do machine learning, in which case you like maximization or whatever. I guess no, RL people like maximization. General machine learning people like minimizing loss functions. They're reasonable. I don't know. It's a weird thing. Okay, so this is, again, scalar valued. And if f is smooth, then we have partial f, partial x equals 0 at a local min. So everyone knows about this, right? Like if you have some f, let's say I'll draw a cartoony one. It has to be flat at the bottom to have a local minimum. Also flat at a local max, right? So, and also flat at a saddle point. We'll get into that in a sec. But the main takeaway here is what this idea lets you do. This idea that like at a minimum, df(dx) equals 0. Now we have a root finding problem, right? So now if I want to minimize a function, I can turn that minimization problem into a root finding problem, which we just talked about. And now I can use Newton's method to solve said root finding problem. So I can use Newton's method to do minimization as well as root finding, because I can transform that root finding problem into a minimization problem or whatever. So now we have this problem. So we can just do Newton on this. Okay, so specifically in this case, we're going to do the same Newton-y thing. We're going to do this. We're going to approximate this with a Taylor expansion. It's a first order Taylor expansion of this equation, which is already the gradient though, right? So it's going to be the Hessian that shows up as the Jacobian, right? So it's this. I'll write it out sort of the way we did before. So we do that. This guy, right, is the Hessian now of our f. The reason the Hessian shows up, right, is because we're doing root finding on the gradient. That's sort of why it's the Hessian. And then we just kind of do the usual Newton thing. So it ends up being minus inverse Hessian times the gradient. And then we do our update. And then we do our this guy. Okay, so let's think about this a little bit more. What we're kind of doing here, so we can interpret this as like, Newton, like we just did. In this minimization context, there's a little bit more interpretation we can like layer onto this thing, right? So now we're talking about Hessians and gradients, right? So what you're kind of doing here, the intuition for this guy is that I'm going to fit a local quadratic approximation to f of x. And then it turns out I know how to exactly minimize quadratic functions, at least convex quadratic functions. We'll get into this too. then I can exactly minimize the quadratic. Okay, cool. Questions about that? So what I'm basically doing, right, is I'm like picking a point on my big function. I take second order Taylor expansion. That's a quadratic. Quadratics, at least convex ones, that's a bowl. A quadratic is just a big bowl, right? So it only has one local minimum, one global minimum. And I know how to do that in closed form using linear algebra. And so I do that. I fit a bowl. I minimize the, I go to the bottom of the bowl exactly. Now I evaluate my function at this new point. It's probably not at the real minimum. And I do the same thing over again. I fit a bowl locally, minimize the bowl, and keep trucking. That's like sort of the intuition behind what this is doing, right? Okay, so we're going to do another example here. We're going to try minimizing a slightly nonlinear function. We're going to try this guy, x to the fourth plus x cubed minus x squared minus x. I'm going to write this down, and then we're going to look at the code and play around with it. Okay, where'd code go? Here's code. Here we go. Okay, we did root find, and we're doing this now. Okay, so there's the f that I just wrote down, and just because it's simple and like, relatively benign, I'm going to go ahead and like diff it by hand because I can. This is a 1D function. This is easy. So there's the gradient. I just like, again, simple. And this is the Hessian. I just wrote these down because it's 1D and it's easy to write by hand. Okay, cool. I'm going to go plot this. And we can take a look. So there's our function. I'm trying to minimize this guy, right? Note it has a few flat spots. It has a couple local optima, whatever, local minima, one local max, right? Okay, and then here's my Newton step, exactly what we just talked about, right? Inverse of the Hessian, and we use backslash. We don't actually write out, inverse of a matrix. That's bad for numerical reasons. Use backslash. Hopefully you guys know that. Let's see, where am I going to do this? So we're going to start over here. We're going to run Newton's method. So there's our starting point. I'm now going to run like iteration by iteration. We're going to plot this, right? So there's the next iteration. I moved from here down to here, already pretty close. And basically, as we saw, like with the last example, it converges really fast. So this is like 2 steps, and like basically by 1 more step I'm there. And like if I keep running this, it's not really going to change. So like 3-4 iterations, I nail it to machine precision, kind of like before. So this is not a surprise. I start here, I land in kind of the closest, kind of local minimum. Let's try another point. Let me try back here. So maybe I'll start at like minus 1.5, and we'll watch what happens there. Oops, minus 1.5. Live code. Okay, cool. So we're going to start here. What do you guys think is going to happen? It's probably going to go here, right? So again, it says local. It's fitting a local bowl to the function and going to the bottom of that local bowl. If I do that here, I'm going to get a bowl that looks kind of like this, right? Based on the Taylor expansion. And so like what we expect to happen is it's going to kind of go here. No surprise. Cool. Does that 3-4 iterations again. And we're basically there. It's not changing anymore. Cool. That worked. Okay, let's try another point. I'm going to start over here at 0. So we're going to start right there. What do we think is going to happen? Go here, probably. There we go. Let's see what happens. So it's starting there. What you want to take? Who thinks is going to go right down here? Nobody. You all got. All right. Well, here. We'll watch what happens. It went left. Okay. So and so now it basically went to the local max now, right? Okay. What happened? It's only doing root finding. Yeah.
It makes the local bowl approximation is upside down.
Yeah. So what's another word for that?
Positive versus negative semi-definite stuff.
Yeah. So this is convex is this way. Like concave is this way, right? So if I locally fit a bowl here, exactly, like if I take the second order Taylor expansion here and fit a bowl, it's an upside, but it's a concave guy. And I'm only doing root finding. So Newton's method, the most important thing, right, is that Newton thing we wrote down. It's only cares about doing root finding on the gradient. It knows nothing about max versus min. It's going to go to the closest root of the gradient, which can be a max, a min, or a saddle. And you'll just get the closest one to where you started if you naively do Newton. So there's some like caveats to this. So that's kind of the main takeaway there. So here's what you just said is kind of the money thing. So I'm going to evaluate the Hessian at this point where I started this time, and kind of unsurprisingly, it's going to be negative, right? So that means it's an upside down bowl. Whereas if I plug in like any of these other starting points, right? If I do this at 1, it's positive, right? So that means it's a facing up bowl. So that's kind of the key insight, is that you know, you can basically, you have to be careful, and Newton on its own doesn't really know if you're doing max or min. It doesn't care. So let's do a little bit more on this topic, and sort of like hopefully fill in some. So I'm going to post the code. So just hit your, if you want to like try this. We did like 1 minus 1.5, and then we did 0, and this one ends up maximizing. Okay, so what's going on here? The sort of like takeaway. Newton is only a local root finding method. That's the key. Those words are all key. So local means it's going to converge to the closest gradient equals 0 point from where you started. That's the local thing. And then the root finding means it doesn't care if it's a max or min or a saddle or whatever. So closest fixed point to the initial guess. Can be any of these, right? Doesn't care. Okay, so next thing, yeah.
Is it guaranteed to never like overshoot the closest one to find the second closest?
More on that in a minute. Yeah, so no, it can overshoot, absolutely, right? You can imagine if like the function sort of like locally, you know, is like pretty flattish and then changes sharply, your bowl might look like really flat, right? You might take a really huge step and you might overshoot if the function's wiggly, right? And land in another local basin. You don't want that to happen, actually, for other reasons. Like that actually can prevent convergence at all. You can actually engineer functions where naive Newton will just like bounce back and forth forever and zigzag across the minimum and never land in the bottom. So that's bad. We don't like that. Now we're going to just talk about basically the things you have to do to fix up Newton's method to guarantee A, that it converges at all, and B, that it always looks for a minimum. These are the 2 things we're going to do next. So the first thing is, how do we make sure it goes to a minimum? So we're going to do that real quick. So the key idea here is what are called second order sufficient conditions. The gradient equals 0 thing that we started out with, that's called a first order, i.e. because it's first derivative, necessary condition. So it's necessary but not sufficient. It says a minimum has to have that property, has to be flat, but that's not enough. That could be a max or a saddle, right? So the second order sufficient condition is what we already just kind of said. Let me write this down. This is first order necessary condition. And someone already said it for a min not sufficient. So let's look at the scalar case. So in the scalar case, we got this. Let's think about the pieces of this guy real quick. So this thing is our gradient, right? this minus step sign out front, this is saying, descend, go in the negative gradient direction, right? If I like kind of pretend this is in here or whatever, this is saying descend. And really this thing in here, this whole thing, you can think about this as a learning rate or a step size in gradient descent, right? Like if I just kind of like squint for a second, this is really minus gradient and this is a learning rate, right? If you're doing gradient descent, okay? So this is kind of really getting at like what's going on with that sign of the Hessian, right? So if we have Hessian greater than 0, I get descent, right? It's a positive step length. But if I get Hessian negative, it flips the sign on this whole thing. And now I'm doing gradient ascent, right? Is that clear, everybody? So this is like the key idea, like Newton, you can think about it like this and think about that Hessian thing as like your learning rate, in which case it's got to be positive to take a descent step. And then that was scalar, right? So in Rn, where this thing's a matrix, we end up with kind of these like conditions on the eigenvalues of the matrix. But just like when we talked about stability, same idea. I can generalize this to Rn by looking at the eigenvalues of the Hessian matrix. And so I write it like this. This kind of slightly, my handwriting is not good enough to actually like resolve this, but that's like a slightly curved greater than symbol. If you do it in LaTeX, it's SUCC. And that means positive definite. And that means all the eigenvalues are strictly positive for a matrix, right? Another way to write that down, you might see also is del squared F in Sn plus plus. So S means symmetric matrix, N for n dimensional, and then plus plus means positive, strictly positive definite. 1 plus means positive semi-definite. Also positive semi-definite, you write this with that equal, greater than equal to sign sometimes. So this means descent. If you have a strictly positive definite Hessian, all eigenvalues are positive. It looks just like that scalar case in all the eigendirections, right? And then we say also if you have Hessian strictly positive definite everywhere. So like we saw in the last example, right? In the example we did, right? The Hessian was positive in some places and negative in some other places, right? Where it's positive, you get nice local descent. Where it's positive, you get local ascent, and that's kind of annoying. If it's positive everywhere, then we can say f of x is a strongly convex function. And basically, like practically what this means, if you have strongly convex function, it means you can always kind of apply Newton's method and you'll always get the global optimum. So these are the functions where Newton like just totally kills on. And this is kind of why we like convex optimization problems and why we do convex MPC and all this kind of stuff, is because we can like get the answer in like a handful of Newton steps and basically always solve them. And then kind of the sort of obvious thing is that this is usually not true for sort of hard nonlinear problems. But sometimes you get lucky. Okay, cool. So any questions about this? Cool. Okay, so now the sort of what do we do when this is not true in practice? The answer is you do something called regularization. It's a simple idea. And basically what it says is this is what we do if we want to make sure, guarantee we're minimizing all the time. It's super dumb. Literally what you do is you start out with the Hessian, And then you check to see if the Hessian is positive definite. So while it's not positive definite, you add a multiple of the identity. So we'll call this like beta I, where beta is some scalar, positive scalar. You do, what the hell? Okay, go away. Okay, so we do this until H is positive definite. Oh, I meant to do H plus. And then you do your Newton step once you've guaranteed that this thing's positive definite. This. Okay, so this is called regularization. This whole thing, you know, in Newton's method is also sometimes called damped Newton. A damped Newton method. So the idea here is what you really want to do is, so yeah, like how big does beta have to be? You want to say, like how big do I have to make beta here to like get this to happen in terms of like the Hessian? So can I see that? It's got to be bigger than the most negative eigenvalue, right? Basically, it needs to pop that guy above 0, right? So the other thing that this is doing is it's shrinking the step size that Newton takes. Like another way to think about this is what this is basically doing is adding a quadratic penalty on delta x. So it's making delta x smaller. So it's basically making your steps more conservative. That's why it's called damping. It's like damping your Newton step. So this guarantees descent and shrinks the step length. Okay, cool. So now we're going to go look at this again. And we're going to do this. So here's the regularization idea. This is a very dumb implementation of this. But yeah, I literally am checking if this thing is positive definite. And then I'm going to pad it with this beta thing. I set beta equal to 1. Again, this is totally arbitrary. Sophisticated good versions of this do fancier things where you like adapt the beta and you never do this. You do smarter things to check. So on a big problem, like checking this is positive definite is super expensive and you don't do it this way. Caveats, right? But this is kind of the basic idea that'll work. So now I'm going to start it in that spot, the same spot where we, sort of last time got some bad behavior, right? It went here. Now with this regularization, you're going to see it kind of do the thing. So, oh, look, who asked about overshooting? Look what happened. I overshot. But now we know from over here, we're in the basin of this guy where it's a negative definite Hessian. So it turns out this will converge, right? So cool. Now I'm back to the other case. So this guarantees that I point my descent step in the descent direction, but I still have this overshoot problem potentially, right? Which we kind of talked about. So we're going to talk about that. So this is the regularization idea. Let's see what time is it. We have some time. Okay, maybe we'll do this. Okay, cool. So everyone cool on that? That's regularization. Yeah.
If you start, even with regularization, start close to the other, or still go to the other.
No. I mean, all this is going to do is make sure you go downhill. Nothing else. It's still always local. It's going to go towards the closest fixed point. And all this makes it do is go towards the closest local minimum. Guarantees you're going downhill. That's it. Right? Like literally all this is doing is taking a Taylor expansion at a point, right? And fitting like a bowl at the point. So it doesn't know anything about what's going on past that, right? It's only looking at this very like myopic local picture based on a Taylor expansion. So it's like inherently local, right? It can never do anything smarter than that. Like hop over to the next basin of attraction or whatever, right? Okay, cool.
Is it related to BFGF?
No.
Well, it is the same edge approximation for Hessian, right?
It is not related to BFGS.
Okay.
Okay, cool. So back to this thing. Bam. Okay, cool. So we did this example thing again. And my pen's not working. I should have charged it while I did code, like I said I was gonna. Right. Okay, so now we always minimize. That's good. Anyone have any questions while I wait for my pen to charge? Yeah, what's up?
Like for like machine learning stuff where you already integrated the set, like have they not adapted like VFGS where you approximate that?
So yeah, you would think they would. It does get used in some large scale regression problems. Like people use LBFGS for sure. It turns out that pretty much all these like accelerated first order methods like Nesterov and Atom and whatever, the lightest flavor of the day, this is beyond the scope of the conversation for today, but those are basically all approximations of LBFGS with like memory 1 or 2. So LBFGS, you would expect like LBFGS with more memory, right? Like with like memory 10 or 20 or 50 or whatever you can handle on the size problem you're dealing with would do better than those methods, right? But they mostly don't do this in deep learning. I think in general, right, those things are just so big that even storing like that, like basically the complexity of LBFGS increases linearly with the size of the memory. So like if you're barely getting by doing like, you know, Atom, like adding 10x to that, you know, to doing memory 10, you know, is probably going to kill you. I don't know, right? It just depends on the problem. But certainly for smaller problems, it makes a lot of sense. And there is some precedent for doing that. Yeah. Yeah. No. TRPO is like a trust region policy optimization. That's a separate idea. So the trust region idea is essentially, so we didn't talk about trust regions. Like I don't think we're gonna, but basically a trust region you can think of as actually like basically an adaptive regularization. So we talked about how the regularization like shrinks your step size. A strict trust region, which actually TRO doesn't do, or TRPO doesn't do. TRPO literally does this. So it's almost a misnomer. Like it's not really doing a trust region. It's doing like a soft approximate trust region, which is just regularization. So it's really just doing this. But a real trust region is where you say, I want to find the best descent I can within a certain fixed step distance. And that step distance is called a trust region. And it turns out the math works out that the trust region equation looks exactly like a quadratic regularizer with a very particular value of the regularization constant that's determined. Basically, it turns out the beta in here in a trust region method, the beta ends up being a Lagrange multiplier for the trust region distance constraint. It's not obvious. You have to write out the math. But if you write out basically a quadratic distance constraint, like norm of delta x less than equal to blah, the Lagrange multiplier associated with that distance constraint ends up showing up exactly where beta does. And you basically solve, you solve for the particular beta that gets you exactly that step length associated with the trust region as a coupled thing. TRPO doesn't do that. That's how a real trust region method works. TRPO is like a weirdo approximate trust region thing. It's really just a regularization. Anyway, end of rant. Hopefully the pen works again. Okay, cool. So what do? We just, let me sort of finish that thought. We're done at 10:30, right? Or 11:30. I mean, we got 2 more minutes. Yeah. Okay, cool. I always, for whatever reason, like get it stuck in my brain. It's like 11:20. I've done this now for like 2 years, and it's a problem. Okay, so anyway, okay, so we did this example again. Same thing, basically, you know, now we always minimize. But we can overshoot. So let's talk about how to fix that now. So there's a couple ways actually to fix the overshoot problem. One of them is a trust region. That's one of the options for fixing overshoot. You basically shrink your trust region so you don't step too far. There's another way to go, which is, I would say, probably more common, which is a line search. So trust region, you fix your step to be less than some fixed radius away from your current point. Line search, you basically find the Newton direction, you try the full step, and then you backtrack until you get a good descent. That's kind of the idea. So often delta x from Newton is too big and overshoots the minimum. And at the end of the day, it's just coming from the fact that your Taylor expansion is a local approximation. And if the function's very wiggly, it might, sort of, that might not be a great approximation. So what we do, we're going to check the step. So we're going to check f of x plus delta x and backtrack until we get a good reduction, all in quotes. What does good mean? So there's many ways of doing this. I'm going to show you the simplest one that actually works, basically. And by actually works, I mean the simplest one that like provably converges. Basically, you can do dumber things, and they might kind of sort of work some of the time, but they're not guaranteed to converge. This one is guaranteed. There are much fancier ones. This is called the Armijo rule. So the idea is we have a step length alpha. So alpha equals 1 means full Newton step. Literally all I'm going to do is multiply delta x inside there by alpha to shrink it. So that's what I mean by backtracking. And then I'm going to do the following thing. While f of x plus alpha times delta x is greater than. So what I'm literally doing, the whole idea behind Armijo is I used a Taylor expansion to compute delta x, right? So what I would like to see is I'd like to see f at my new point. Like I'd like to see the decrease in f at my step roughly agree with the Taylor approximation, right? That's kind of the core idea behind this thing. It's saying I want the decrease I see on the real nonlinear function to roughly agree with the decrease I expected from the Taylor approximation. And if those roughly agree within some tolerance, that means my Taylor approximation is like valid there, and this is a good step. If they wildly disagree, it means I stepped too far and I stepped outside the realm where my Taylor expansion was a good approximation to the function. So I'm in like sketchy territory and I shouldn't do that. I should backtrack to where things are safe and my Taylor approximation agrees with the function, right? That's the intuition behind this. That's what it's trying to do. So it will also backtrack if it gets more decrease than it expected, right? So that's the idea there. You want to stay in the territory where thing is like, things agree with the Taylor expansion. So in particular, this is called the step length, right? AKA learning rate, right? If you're a machine learning person. Okay, so this is the Taylor expansion. So so this is B, which is some tolerance, times alpha times grad f of x times delta x. So this is the expected reduction given a first order Taylor expansion of the function. Notice here, I'm using only the gradient. Right? I did Newton, so there's fancier versions of this that use the gradient and the Hessian and see how well the descent agrees with a second order Taylor expansion. That's more complicated, which is why we're not doing it. This is called the Wolf conditions, if you want to look into that. But there's way more subtlety there, so we're not going to do it. This works though. So this is expected decrease from gradient. So while this doesn't agree within some tolerance, we're going to chop alpha down by some factor C less than 1. And then basically you just keep doing that. So the intuition again is make sure step agrees with the linearization to within some tolerance. Which is B. So this guy's the tolerance. And so typical values when you do this in practice for these like constants. So usually we set C, the like backtracking parameter, to something like a half. So we just chop the step length in half every time. And then B is usually actually quite small, like something like 10 to the minus 4 to like maybe 0.1. So the tolerances are pretty loose, is I guess the message. But it turns out just checking that you get a decrease isn't good enough to guarantee convergence. You have to have this like extra like gradient tolerance term, even if the tolerance is really loose. Okay. Do I have code to show you this? I do. I have to find it though. Because that lets you overshoot the other way. So you can imagine if I have a function that like basically like does something like, I don't know, let's see, what's a good way to talk about this? I mean, essentially, like the heart of this is you don't want to step past where the Taylor approximation is good. Either way, right? It's saying like what this is doing is just making sure you're not stepping too far relative to the Taylor approximation that you made at your last point. And it's like the argument is that that's just bad no matter what.
So does that end up with problems with constraints? Like it seems like down the line, deeper.
So yeah. So this is absolutely true. Basically, to deal with, we'll talk about the constraint case. Essentially, what happens when you have a constraint is you make a thing called a merit function, which is like basically includes like this f plus some like constraint violation term, and you have to make sure that that whole thing decreases both the objective and the constraint violation, like norm of the constraint violation or something like that, and then you just do the same thing. Okay, so let me get you the code real quick for this guy. Cool. Okay, here we go. Same stuff. So we did last time. Oh, crap. Okay, we don't want that. Give me a sec. It's going to take forever. Apologies. I didn't think we were going to get this far. Okay, hopefully this isn't super mad at me. Cool. Okay, I think we're okay. Ah, God damn it. Don't do this to me. All right, I think this is gonna take forever. Sorry. That's basically it. I was just gonna show you the line search thing working. So if I can get this thing to not suck, I will do that for you. But yeah, that's it for today. I promise it'll work. It just might take several minutes for it to decide that the package manager is happy. Okay, it looks like we're gonna be okay. Cool. All right, cool. Yeah, we're in business. All right, so here's what we did last time. This is the plain Newton thing, blah, blah, blah. Here's the same stuff. Okay, here's the regularized thing that we just did where it overshoots. So there's that kind of overshoot behavior. but then it's cool. Here's backtracking line search. So we're doing the regularization. We still have to do that. And now on top of that, we're going to do the line search. So here's the line search exactly as I just wrote down with parameters like for B.1 and whatever, C half, like we just talked about. Now, with all that stuff, same starting point where we overshot last time. Let's look what happens now. Hey, look at that. Nice clean descent towards the bottom. And now we converge in like a couple iterations like before. Okay. And we did it. I almost got my technology to work for the day.